Hello everyone. In this session, we are going to discuss about the concept of virtual memory, which plays an important role in the memory unit, a memory system. And we will just start the discussion with respect to the diagram available here. Okay. So as a user, when we write the program are supposed to be saved in the secondary storage, and this secondary program available in the secondary storage has to reach the processor across different levels. So we are just going to see the memory is going to be organized in different levels. And before that, we know that the CPU is going to execute the instruction in four phases. Okay. So the four important phases in any instruction execution process is that fetching the instruction. Okay, then we have to decode the instruction. Only after decoding the instruction we will come to know whether it needs operand. If it is going to involve operands, then we have to calculate the address of the operand. Okay, and if after calculating the address of the operand we have to fetch the operand also. After fetching the operand we can directly execute the instruction. When the CPU executes the instruction, it will get the result, and the result will be stored and it has to be written back into the memory. So any instruction execution in processor has to follow these four stages. This point I think already we have discussed. Just I have refreshed the point here. Now if it is going to fetch the instruction, where from it is going to fetch? So fetching the instruction and fetching the operand is going to be from the memory. And in which memory it is going to refer to? Always the CPU will always refer to the memory which is closer to it, and as such the processor will also have some registers inbuilt. It will just look for the data in the registers available inside the CPU. If it is going to be instruction, it has to be fetched from the cache memory. So the next level of memory will be the cache. If it is present in the cache, if it is a hit, it will use the data directly from the cache memory. If it is not there in the cache, then usually it is going to be called as a miss, and because the data is not there in the cache, it will look into the main memory. And again, if it is going to have the data, if it is going to be a hit, then okay, if it is going to be a hit, it will be supplying the data to the cache memory, and then from the cache memory it will reach the processor. Suppose if it is not there in the main memory, obviously it has to look to the next level. So if the requested item is not there in the main memory, usually this is going to be a miss, and this miss is going to be called as a page fault. What I mean by page fault is the page requested is not available in the main memory, so it is going to be a page fault. This is also a scenario which depicts the situation of miss. And if it is not there in the main memory, it will refer to the disk storage. If it is present in the disk storage, it will use it, so it has to be moved on to the main memory. As we all know, the secondary memory is going to be the huge size. Okay, we will be transferring huge volume of data. If we want to transfer huge volume of data from the disk to the main memory, the CPU has to intervene in this operation. CPU is totally meant for doing only processing. Now what we are trying to do, we are trying to use the CPU for data transaction, IO activity. So in order to effectively utilize the CPU, we are not going to disturb the processor for doing this transaction. Instead, we are going to make use of the DMA transfer. So what actually we mean by DMA transfer is direct memory access transfer. So we are trying to allow the IO devices to access the memory directly without disturbing the CPU. So at a faster rate, the data transaction will happen between the secondary memory to the main memory. And once it has reached the main memory, then the CPU will be able to use it only from the reference to the cache. So it has to be again transferred to the cache memory, and from the cache, then it will reach the CPU. So at this point of junction, we are just exposed that we have different levels of memory. So in memory hierarchy, what are the different levels? If you just observe, the first level is going to be the registers which are available inside the CPU, and these registers are fixed in number. They cannot accommodate the whole data required for your application. So whatever is possible, that alone will be stored in the register. Since it is closer to the CPU, it will be executing, the processor will be referring to the data available in the register and executing at a high speed. If register are not able to accommodate all the data or instruction, it will be kept in the cache memory. Again, the cache memory, it is going to be available in three levels, that is otherwise identified as level 1 cache, level 2 cache, and then level 3 cache. And not only this classification, the cache memory is also going to be classified into two categories. One is called as unified cache, another one is called a split cache. Unified cache, split cache. So what do you mean by unified cache? Unified, Okay, that means both are same, or that means we have the same cache to store the instruction and to store the data. So if I use a common cache to store both instruction and data, it is going to be called as unified cache. In order to do some parallel activity, I will separate these information and store the instruction in the instruction cache and store the data in the data cache. If this is going to be adopted, then it is going to be called as secondary cache. Okay, sorry, this is going to be called as split cache. Now, after referring to the cache memory, then the next level, what we are going to see is going to be the main memory, and then after this main memory we have the secondary memory. Okay, and as we move away from the processor, these levels are going to have increased capacity and reduced speed, and also the cost also will be decreasing. Okay, so now across these different levels we are just going to compare in terms of three parameters, namely the speed, okay, namely the speed, the cost, and the size. All these three parameters are going to be important, and they are going to vary across different levels. Suppose if I claim like this is going to be the registers, first level is the registers, then the we have the second cache memory, then we have the main memory, then we have the secondary memory. If I just organize the different levels in this direction, then if I just go towards the CPU from the from the farthest level to the innermost level, the speed is going to increase. Okay, that means if I compare the speed of the disk storage, it is going to be less when compared to the speed of the cache, or when compared to the speed of the registers. So as we go deeper or nearer to the CPU, the speed will be more. And what about the cost? Obviously if the speed is more, the infrastructure has to support that facility, and obviously the cost also will be high as I go nearer to the CPU. So if I just compare the speed and cost, they are going to be directly proportional as I go nearer to the CPU. Coming to the size, because it is expensive, because the level of memory near to the CPU is expensive, the size we are not able to provide huge size. The size will increase only in this direction. As I go away from the CPU, the size is going to be huge. Okay, so if I compare the memories across these three levels, we can have these three parameters: speed, cost, and size. As I go nearer, the speed will be fast, and as I go nearer, the cost of the storage unit will be more, and the size will be less. Okay, so these are the three important parameters that has to be associated with different levels. Now coming to the concept of virtual memory, here I have to store my program and data. That means my application is going to be restricted to the size of the secondary memory. If my application is going to be greater than the size of the secondary memory, then what the CPU will do? Will it deny my application? That is not usually expected. So for that purpose, what we have done, we just introduce one more level of memory, which is going to be called as a virtual memory. As the name implies, this concept is virtual. That means there is no physical memory available with me. So we have the concept of virtual memory, and there is no boundage for the size. Okay, now how we are going to make use of the virtual memory which is not physically present, then how can I make use of it? Okay, now to appreciate this principle, we have to first understand the processor behavior. If we observe the CPU at any point of time, the reference pattern followed by the CPU is going to be confined only to some local space. Okay, and because it is confined to local space, at any point of time, the information available in this space, if that is alone made available to the CPU, the CPU will be able to execute it. And if my application is going to demand more such space, then what I will be doing, I will be partitioning my application into different fragments. Okay, and what I will be doing, I will be loading the first fragment into the secondary memory, then transfer it to the main memory, transfer it to the cache, and then get executed. And once the execution of the first partition is over, I will throw it out, and then I will take the second partition. Okay, then I will complete, after the CPU completes execution of the second partition, it will throw it away and then load the next partition. Like this, I can just make the CPU to execute partition by partition, and by means of this concept, I am not restricting my application to a physical size. Okay, so though these partitions are not readily available within this secondary memory, it can be stored somewhere. Somewhere means it can be stored in the cloud, or it can be made available in other secondary memory. So it is, if it is a hard disk, I can use second hard disk, I can use third hard disk. So The purpose of having this virtual memory concept is the CPU is not restricted to execute an application whose size is restricted by the secondary memory. If my application size is going to exceed the secondary memory size, still I will not say no, that I will make the partition, load the partition in the secondary memory, then I will be executing. So to appreciate the behavior of the CPU reference pattern. That's what this reference pattern is otherwise called as locality of reference. This is a key property of the processor which introduced the concept of locality of reference. So this key property of the CPU only invented the concept of virtual memory. At any point of time, the CPU reference is going to confine to local space, and because it is confined to local space, I need not restrict the application size to be big enough, okay, to suit the size of the secondary memory. So even if the secondary memory is not able to accommodate my full application, I will load one partition alone as the reference pattern is kind of confined to this partition alone. After completing the execution of this partition, I will throw the CPU will throw it away, and then it will bring in the second partition. Like this, which partition to be brought in, which partition to be thrown out, all it is going to be decided by this MMU, which is nothing but the memory management unit. And as we see different levels of memory means it is going to store some data. So each location in the memory will be having some data or some instruction, and this location has to be referred by means of giving an address. Okay, so if I am going to refer an address which is physically present, then that is called as physical address. If it is not physically present, then it is called as a virtual address, or the other name for this address is also identified as logical address. So you have to understand two type of addresses. One is a logical address or virtual address, another one is physical address. Any address which is going to refer to the memory which is physically present, then it is called as physical address. So if you just observe here, the cache is physically present, the main memory is physically present, the disk also physically present. So all the location in these memories are going to have some physical address. And if the user is going to develop an application, develop the program for the application whose size is not restricted and whose content may spread across different secondary memories, or it can be made available in the cloud storage, then all the addresses referred in those spaces, that is going to be called as a virtual address. So now we are just referring to the two concept of one as a physical address, another one as a logical address. As a user, when we write the program, we will be referring to the logical address because we don't know in which memory it is going to be loaded, and in that memory in which location it is going to be loaded. Now when the CPU executes information from this cache memory, the reference address will be different. So if it is going to be the cache memory, it will be referring to the cache address. If it is going to be referring to the main memory, it is going to be the main memory address. Okay, and then if it is going to be referring to the secondary memory, it is going to be secondary memory address. And if it is going to be referring to the virtual memory, it is going to be a virtual memory address. Okay, so the address is going to vary in each level. So the same information brought across different levels, it will just pass on different addresses. Now how these address references are going to be managed, and the memory management unit is very much responsible to translate the logical address into the physical address. The CPU will always generate or refer the logical address. It has to be converted to the respective physical address based on the availability. If it is stored in the cache, where it actually is stored, that address is called as a physical address. So every time the memory management unit has to do the mapping of the logical address into physical address, and this physical address can refer to any of these three levels. The virtual address or the logical address always refers to the virtual memory, the one which is not present in this setup. It may be available as a third secondary storage, or it can be made available in the different cloud structure. So in this diagram, we have discussed the concept of different levels of memory hierarchy, how these memories are going to be, levels are going to be associated with three parameters, namely the speed, cost, and size, and how the address is going to vary. We will continue the rest of the discussion of this virtual memory.
Hello everyone, I welcome you all to this session to discuss the concept of virtual memory. In the previous session also we have discussed virtual memory, where we have seen all the levels, different levels of memory hierarchy, and how the memory address from one level to another level varies, and how the data transfer happens from one level to another level. Now as a continuation of that, we will just move on to contiguous memory allocation and non-contiguous memory allocation. So whenever there is a request from the user process, the memory can be allocated either in the continuous fashion or in the non-continuous fashion. And when it is going to be non-contiguous, then we have two different techniques there. One is called as paging. Another one is called as segmentation. In paging, we are going to divide the entire memory into fixed pages. Whereas in segmentation concept, the memory is going to be divided into varied sizes. So fixed partition means paging, and if it is varied partition, it is segmentation. Now, if you just observe this, here we have this concept of main memory, which is divided into so many units, so many partitions, and each partition in the main memory is going to be referred as frames. Whereas if it comes to secondary memory, again the secondary memory is also going to be partitioned into different units, and this each unit in the secondary memory is going to be called as a pages. So one unit in secondary memory is referred as pages, and the same unit available in main memory is referred as frame. And one important point to be observed is that the frame size and the page size are going to be always equal. Now we will just see how actually the memory is going to be referred in terms of addresses. In the previous discussion, we have talked about logical address and virtual address. Logical address is nothing but the address generated by the CPU for its reference, whereas the virtual logical address can also be called as a virtual address. And that information, whatever we are referring to, it might be available in any of these memory levels. If it is available in any one of the physical level memory, then it is going to be called as physical memory. We will just see how this address is going to be translated into logical address, how it is going to be translated into physical address with the help of this diagram. So if you just observe this diagram, I think here we have the partitions, and already we have discussed that the memory is going to be having different partitions, and in the memory hierarchy we have discussed, maybe just we will just see this diagram here. We have the CPU, we have the concept of CPU, okay, and inside CPU we will be having the registers, which is going to be in the lowermost level, and the next level of memory is going to be cache memory, and this cache memory can be level 1 cache, level 2 cache, level 3 cache, and then the next level will be the main memory, which is going to be huge in size compared to cache memory. So this is going to be the main memory, and then the next level of memory is going to be the secondary memory. And secondary memory, when you compare the size, it's going to be still more huger than the main memory. And then after the secondary memory, we also have the concept of virtual memory. So this is going to be the overall hierarchy of the memory. And as far as the secondary virtual memory is concerned, the size is not bounded, so we have unbounded size, okay. It is not a fixed size. Now, whenever the CPU wants information, it will refer in the registers, or it is not there, it will refer to the next level, like this. It will keep moving from one level to another level. Instead of virtual memory, we can also have multiple secondary devices. Now, each memory is going to be partitioned into different units, and each partition is going to be called as different units. Suppose, for example, if we consider secondary memory, the secondary memory is going to be partitioned, and each partition in the secondary memory is going to be called as pages. And when it comes to main memory, each partition is going to be called as a frame. And when it comes to the cache memory, the group of locations inside this is going to be called as a block, okay. And then when it comes to registers, it is going to be line. So if you take pages, the pages can contain so many words, so many words can be there in a page. Similarly, in a frame, there can be so many words, okay. And if you take cache memory, there could be so many lines. So the number of words inside this cache memory, this is going to be called as lines. So you have to understand the basic unit of reference. And in registers, it is going to be called as a word, okay. So if we just to recollect again, the secondary memory divided into so many pages, and each page is going to have some group of words. Similarly, main memory is going to be identified with frames, and each frame is going to be collection of words. When it comes to cache memory, each word is going to be called as a line, and collection of such lines are grouped together to form block. And then coming to registers, each location is going to be called as one word. So this is going to be the basic unit. And as a user, when we write the program will be available in the secondary memory, and all the addresses that is going to refer to the secondary memory or to the virtual memory is going to be called as a logical address or virtual address. So this logical address or virtual address is going to have two components. So the address which is generated by the CPU is going to be called logical address, and it is going to have two components, one the page number, and then the second one is the offset. So what do you mean by offset? So if you take one page, within this page, uh, the word which I am just referring to, so this word if I am referring to, so this is going to be called as an offset. So the distance from the beginning of this page to the desired location, this is going to be called as offset. Okay, so any logical address will have two components, page number and offset. So this logical address needs to be translated into physical address. So whenever I move my page into the secondary memory and then into the main memory, then in the main memory in which this page can be placed in any of these frames. So in which frame it is going to be placed, that is going to be maintained by the page table. So in page table what we are going to have, we will be just having all the page numbers and the respective frame numbers. So from this what we can understand, the page number P1 is loaded into frame number F. Okay, so this detail will be available in the page table. Now we have to convert the logical address into physical address. As I already told, logical address is having two components, page number and offset. In the same way, the physical address also going to have two components. One is a frame number, another one is the offset. So whatever is the offset we are having in the logical address, the same offset is going to be copied. Why? Because we already know the frame size and the page size is going to be the same. Since these two sizes are same, if I take a particular line in one page, the same line will be followed in the frame also. So due to this reason, the offset is going to be the same. So I am going to copy the offset as such. Now my reference pattern is going to map the page number with a frame number. So the mapping of the page number to the frame number is available in the page table, and I have to search through this page table, and wherever I find this page number 1, the respective frame number is going to be taken and it is copied to form the physical address. Now as such, if you take the memory, there could be so many such page tables available. So my required page number, whether it is available in this page or another page, that is going to be decided by the page table based register. So as the name implies, this page table based register will always hold the starting address of the page. So if my page number is, suppose for example, if it is 17, and if this page table based register is not going to have this 17 as a starting address, then I will just look into the respective page table based register. Each page table based register will have the respective starting page available in that page table. If this page table is not going to have this information about the page number 17, then I have to look into the next page table. So each page table will have its own starting address, and that starting address will be loaded every time into the page table based register. So whatever is the page number I am getting from the logical address, this along with the base address, that will give me the respective page number, and if that page number is present in the memory, I will obtain the respective corresponding frame number. So this frame number will be copied to form the physical address. So memory mapping or translation of the logical address into physical address, what actually it means is that we are trying to convert the logical address into physical address. So the logical address is nothing but the address which is available in the secondary memory or in the virtual memory. Once that information is loaded into the main memory, the respective frame number will be updated in the page table, and by looking into this page table, it will be possible for me to identify in which frame my desired page is available. If I obtain the frame number, whatever is the offset available in the input logical address, the same offset will be copied, and thereby I will be able to generate the physical address. This process of translating the logical address into physical address is called as translation, address translation. And if you just observe, every time when the CPU refers to an information, it has to provide the logical address, and once it wants to fetch that information from the memory, it needs a respective physical address. So every time the logical address is going to be translated into physical address. If the same instruction is going to be repeatedly referred, and for every references if it is going to be translating, then it is going to be a time consuming work. In order to minimize this time, what actually will happen is that there is a concept of called TLB. What I mean by TLB is nothing but translation look-aside buffer. So what is this? This is nothing but, as the name implies, translation look-aside buffer. So it is like a kind of a buffer. Buffer means what it will do, it will store something which is going to be frequently referred. Okay, so in this buffer we will be having, in this buffer we will be having the translated address. So if I refer to a particular line in the memory to identify its physical address, I have to do the mapping. And if this mapping has to be done for every references, it is going to be time consuming activity. So for one time, for the first time, if it is available in the memory, I will do the translation, and the translated address details will be stored in this buffer, and I can, as a CPU, it will just first look into this TLB, translation look aside buffer. If it is available, it will try to fetch that information from the respective physical address. If it is not available, it will do the mapping, and if in case in future if the same information is going to be referred, to make it easy, we will update the translated address in the translation locusite buffer. So we have just discussed about page table and TLB. So page table is a concept which will maintain the mapping of the page number with the respective frame number, and like this we will be having multiple page table. Each page table will have some starting address. That starting address will be updated in the page table base register. So to locate the desired page, I have to add this base with the logical page number available in the logical address. That will give me the respective page number. If it is there in the memory, I will be able to get the frame number. If it is not there in the memory, it is going to be called as a miss, which is otherwise referred as page fault. I think that we have discussed in the previous class itself. So in this session, we have just identified how the memory address, logical address, is going to be translated into physical address, and how actually this mapping is going to happen with the help of the page table. And we have also introduced the concept of TLB, which is going to be an important and frequently asked question, translation look aside buffer. As the name implies, it is a buffer which is going to store some information which is going to be frequently referred. That information is nothing but the mapping of the logical page number to the physical frame number. That mapping information will be made available in the TLB, which can be looked ahead in order to do the translation. So this completes the discussion of this virtual memory part 2. Thank you.